This is the screencast for section 6.1, example 10. We're going to move backwards with Euler's method. So same process as regular Euler's method, it's just now we're going to start out with a point and try and estimate a y value using a smaller x value. So we're going to go backwards to the left. So in this case it says if dy dx equals 2x minus y, and if y equals 3 when x equals 2, use Euler's method with 5 equal steps to approximate y when x equals 1.5. Alright, so they give you an initial point, 2, 3. They don't give you delta x, but they do say that we're supposed to estimate the y value when x equals 1.5, and we're starting out with 2. So the difference there is 0.5, and we're supposed to do that in 5 steps. So to get through a distance of 0.5 in 5 steps, my delta x is going to be 0.1. Now we are moving left this time, so I'm going to move backwards 0.1, and my delta x is going to be negative 0.1. Now dy dx is going to be 2 times my x coordinate plus or minus my y coordinate, so I get 1. Again, we're moving backwards, so my x is negative 0.1. My delta y is also going to be negative then, so I take dy dx times my delta x, and I still get negative 0.1. So now I'm going to take my x coordinate and subtract 0.1, my y coordinate and subtract 0.1, and my new point is 1.9 comma 2.9. So that is back here in red. Alright, let's keep going. We'll take that 1.9 comma 2.9, calculate the derivative there, which is 0.9, the slope of at that specific point. Then we'll do a delta x of negative 0.1. Again, we're moving backwards another 0.1. That means our delta y is going to be 0.9 times negative 0.1, which is negative 0.09. And our new point is 1.8 comma 2.81. So maybe back here. And I'm going to keep going. So now with that new point, my new slope at that spot, and then delta x stays the same, my new delta y, change my point by subtracting from x and subtracting from y, and I get another estimate. One more time through the process and I'm at the x value 1.6, yet another time through that process, and I end up with my x value at 1.5, so I can make the statement f of 1.5 is approximately equal to 2.61051. Then now try problem number 45. Says use Euler's method with increments of delta x equals negative 0.1, so that gives you a clue you're going backwards, to approximate the value of y when x equals 1.7. dy dx equals 2 minus x, y equals 1 when x equals 2. So I've got the point that we're going to start out with, 2 comma 1. I can calculate my derivative there, which is, well, 0. My delta x is negative 0.1 that was given, so I know I'm going backwards. So 0 times negative 0.1 is 0, which means my x is going to subtract 0.1, my y is going to stay the same, so my new point, or my estimated point along this curve would be 1.9 comma 1. I'm going to start with that one, calculate the derivative at that spot now. Again, my delta x is negative 0.1 as given by the problem. Delta y is my dy dx times delta x, and then change my new point by subtracting 0.1 from x and 0.01 from y. And now I got yet another point to start out with. Last time through that problem, and finally I have the x value 1.7, so I can make the conclusion that f of 1.7 is approximately equal to 0.97 according to Euler's method.